Full throttle. That's freaking.
Expanded if you'd like. We have 240 batteries total for that setup. We got a couple of them charging up right now. We're going to do a capacity test on that, kind of prove that it is what it says it is. I mean, it's the best batteries that Chinese money can buy. So, but we got our pure nickel strips, which we're going to spot weld all the parallel connections and then run series connections afterwards. We got the spot welder here. We got the BMS over there. So we'll get ready to just put it together and then see what we got.
And so as far as assembling the battery pack, once we get all these tested and everything, what do we have to do? We have to spot weld them all together, right? Or are we hot gluing them together
we're spot welding
first?
them together. First we'll probably hot glue the 12 in parallel, which we then line them all up. We can keep them flat against an edge and get all 12 of those lined up. And then once we have our 12 packs, we'll spot weld across the top to hook them all up in parallel, which what that does is it basically adds the capacities together, but the voltage still stays 3.7 average per each. And then once we start connecting them in, so this is a parallel connection where they're both positive, positive, negative, negative. Once we switch that over, when the battery gets power flowing through this way, it'll end up combining the voltages. So we're going to get all of our capacity added up, which if these are to spec, which they're pretty close based on what I had seen, it'll be right around 40 amp hours with 3.7 volts, and then we'll just combine the voltages until we've ended up gotten the 72 average, which will peak out at 84.
Gotcha. Yeah, so we're going to test out every single one of these batteries. I'm just going to leave you guys to the time lapse. I'm sure you don't really care to test every battery with us, so let's get to it. I'm just going to show you guys really quick what exactly we're using. I know we kind of breezed over it really quick.
That's the battery management system, which was abbreviated to BMS. And it's got enough pins to have wires that lead to 20 different series connections. So we'll connect that up after we get everything glued together.
Okay, then we'll just move on to
these are just what came with the spot welder, but we've got a whole set of brand new. They're a little thicker, pure nickel, transfer a lot of energy, so they'll be super conductive and not have any heat or any heat buildup or energy loss in the process. We got enough. I forget, we got like 30 meters or something. Quite a bit. It was like 30 or 40 bucks worth of nickel.
Okay. Then we got the batteries charging, of course.
Charging up, yep. These are the ones we tested already. We've got 1 3/4 boxes left to go. They're packed in there pretty nice, but
yeah, lots of batteries though, 240 of them.
Yeah, so the Inja is going to keep working on this. I'm going to jump in and start gluing up the parallel leads. So this is going to be 1 series connections worth of parallel connections. So I'm going to just glue these all with hot glue flat with all the negative ends and positive ends lined up the same way. Then we can just spot weld nickel strip across there, which allow all these to basically just piggyback off each other and increase the capacity of each cell, basically.
Cool. I know some of you guys were sending, a couple of you actually sent me a couple diagrams just to help me out. So this is the one we're doing right here. And so I'll let him explain.
I just drew this one up on PowerPoint, and this is basically the pattern that we're going to follow. You got this will be one of the connections that looks like this. We're going to do 20 of these once we got them all tested, make sure the cells are all good. And so between one row and the next, this is the bottom. I got a diagram for both the bottom and the top. But between 1 and 2, they're going to be connected on the back side from negative to positive, and then we're going to come back to the top and connect from positive to negative to the next cells, which between each of these connections now it goes from 3.7 volts to 7.4 volts, whatever that winds up to, then 3.7 more, 3.7 more, 3.7 more, all the way till we get to the end, and it ends up being 72 volts. It'll end up being higher when it's fully charged and lower when it's fully discharged. That's just the nature of batteries. But at each case, it'll have more than enough power to send out 3,000 watts, which I think may have been the problem with what the motor was not getting supplied with enough current. As the turn the throttle, the voltage would drop on the display. So amps and voltage just not quite enough to supply the motor with what it needs. So this will be more than enough for that. And then if it ends up not having enough range, we have the ability to just extend. My original design was 16 in parallel. So 20S 16P, which would have been like 52,000 milliamp hours. But if we run one test run and it gets 50 kilometers, we want to order more cells before we discharge too many cycles and just build on this. And then, I mean, as many as we need to, 20 by 20 or whatever you'd like. This should give, I'm guessing, it should get you minimum 70 kilometers on a charge.
Nice.
But we'll see how it ends up winding up.
Yeah, definitely. Well, let's get to it. He's going to be hot gluing and doing all that jazz. I'm going to keep testing what we got left. Alrighty, well, we finished spot welding 19 of the 20. We have 2 charging still, so we're waiting to make sure those test well, and then we can finish the last row.
Rather than having to lug the whole pack around, I figured we just glue them in pairs, and then we can do, we've got all the parallel connections done, we still got to do series connections. So we can at least do the series connections on pairs, and then have groups that are connected on one side, positive and negative, and then at the end we can start putting the pairs together, weld those ones across, and then so it's not getting super heavy until we've got all the way to the end. So we went ahead and got all the series connections done on one side, so you can look at all these batteries and they're all connected on that side. We're starting off doing the series connections on the top part now. So I'm kind of gluing them in 4 parallel groups now. And what happens now, this is the first set done with the full series connections made. This is the first set of cells, and the power is going to basically flow through. You always start with the one negative, and then your last one you have the positive lead exposed. But you're going to connect the battery here, and then it's going to basically add up the voltage as it flows through from here through, and then it's going to connect on the bottom here to the next negative, and it comes back up, connects on top here, and it flows down, and it's going to basically work its way through the whole battery pack like that until it's gone the whole way through, and then you got all your batteries voltage adding up basically, so that makes 72 volts at the end. And we got a shipment of backup batteries in, so we're going to add an extra row of parallel cells, so it'll be 13P at 20S. Yeah.
And that'll increase range, or is that
It'll
gonna
increase
power?
the, well, range. It'll make it so it has more amp hours, which together will, with the voltage, make watt hours, which is your range.
Cool.
Yeah. So finished up with the blocks of 4. Basically the goal was to be able to start doing this series design without having too heavy batteries to hold and work with. So they're all in blocks of 4 now. So we just got to start putting together some blocks of 8, and if we connect this up, then we've got a full circuit that'll run through 8 of them, and then we'll do another 8, and then we'll add that on, and then ultimately to have all 20 series. Then we just got to add on the bonus we ordered as backups, which we didn't need backups, so now we have extras.
Yep.
And like a 13th parallel line there, but
Yeah.
get ready to roll through.
Finished it. Go ahead, Lord Kirk.
Yeah, and by finished he means we basically got all the series parallel connections in. The last part to go with it that's electrical is put the BMS on, and we got this here ready to go. We'll be working on getting that all attached. There's some balance wires that we'll connect, and I'll sort of talk through how that's all going to look. But for now, we've got to get some wire to run the power, positive and, well, negative and positive leads to this, and to the charger and the output and all that kind of stuff. So we're going to run to Lowe's actually, and grab those real quick, and then we'll come back and get everything soldered up.
And looks like the battery box is going to fit that battery, hopefully no problem, but that's to be determined. All right, we're going to run to Lowe's, and we'll catch you guys when we get back.
Right, so let's just talk through sort of conceptualization, the numbers behind how to go through thinking about the build, and then just like the step-by-step process of what we're doing and what each of the pieces on the battery are going to be doing. So I started it with just designing. I just used PowerPoint, something pretty simple. Top and a bottom of a battery. Ultimately, the battery in front of us matches the specs except for one detail. We ordered enough batteries to have 12 parallel, but then weren't confident that the supplier would have 100% delivery of perfect batteries. So we added an extra 20 in, which would have been able to either fill a whole series in the event that they all worked, or replace a few that had not been, they weren't quality batteries. Turned out they were all good, so we got an extra row. So the one in front of us is 13 parallel. So you can kind of see that there's an extra one added on the bottom, and then we just spot welded in connections to continue the battery downward. As far as figuring out what system to run or that kind of thing, you have to look at the voltage of your entire system, and this one was 72 volt system. So with a 72 volt system, we know that the nominal voltage of any single lithium ion cell, whether it be 18650, 26650, or apparently based on the battery we pulled out, 26800, in any case they're all 3.7 nominal voltage. That goes up to 4.2, and that goes down to 3 when it's charged or discharged. But if you want to have a 72 volt system, all you got to do is take your 72 volts and then divide that by the nominal voltage of each parallel row of cells, which is going to be 3.7, and it tells you we need about 19 and a half cells. Turns out the only options you have are 19 or 20, so I figured the controller can handle a little more voltage, so we're just going to go 20S, which is 20 series in those terms. As far as the number in parallel goes, then basically you have to determine what voltage you want first, and so you figure out the series, and then the other direction, the parallel lineup, just tells you how much capacity you're going to have. So based on the cell capacity, you can figure out how high you want it to be. We wanted ultimately about 40 amp hours, and so we designed it based on that premise. Ultimately what the motor sees isn't amp hours, they see watt hours, so you have to take your voltage times whatever amp hours you're trying to run. So we were aiming about that, which is exactly 1 watt hour for the current motor. So it's 2880 is the actual wattage of the motor. We went a little higher. After all is said and done, we had 3400 milliamp hours, which is 3.4 amp hours per cell. 13 in parallel gives 44.2. So in watt hours terms, that is 3,182 and some odd change of watt hours. And so what that tells me, basically, assuming, aside from some losses that occur at higher drain, your batteries could provide basically 1 hour on a 3,000 watt motor. Ultimately, this motor on there is that, but my hope is that at some point the Inja decides to go 5,000, 8,000, something like that, right? So we're trying to figure out, ultimately the batteries we created will run a 3,000 watt motor super easily for a pretty long time, but I've devised a scheme that'll be able to basically connect each of these series connections and turn them into connectors, so you could just plug a second extension battery in, which I'm hoping at some point as the motor starts to ramp up, you start to see that possibility. The other thing you got to consider really when you're doing this is how much amps each cell is delivering. And generally high capacity cells like 3400 like these are of a lower drain amp rating that they can handle. In some cases it's usually rated in like C1, C2, C. But oftentimes it's just listed as 5 amp drain, 20 amp drain, 30 amp drain. That's a continuous amount of power they can deliver without heating up too significantly. As they heat up, they lose efficiency, risk explosion, and there's other stuff that could go wrong.
Light your house on fire.
Yeah, who knows how it'll turn out. But the goal is ultimately to have each cell delivering an amount that it's rated to drain. These cells were Chinese supplier cells. Every spec that they gave that we were able to verify we did turned out to be correct. The internal resistance was fairly low, and so the amount of drain that they can provide is generally a little bit higher than another high capacity cell. They're rated at 20 amps each, continuous. I realize that's probably an over-exaggeration. As it sits, the run that we've devised, if it's pulling 3,000 watts on the current motor, and we have 13 in parallel, and we divide that by the 72 volts, each one's only asked to pull 3.2 amps, which is not a ton. If you were to up this to a 6,000, I'll say 5,000 watt motor, 5,000 watts divided by 72, that's how many amps it's drawing. Divide that by 13. Still reasonable. If we were to do 8,000 watts, this is fairly well below, and this is less than 2C, that's pretty easy to deliver for generally even a high capacity cell. Once you get to 8,000, it starts to get a little bit, I'm not quite sure about that. So if we divide this by 72, that's the amount of amps it's drawing. Divide that by 13 cells in parallel. I don't want to subject these to over 2Cs for a significant period of time. So if he's doing an 8,000 watt battery, and aside from getting more range out of an increased battery add-on, you'd be getting more safety, cooler runnings of the battery. So my guess is, if he's looking to go 8,000, which is over the specs that they're originally delivering, that's over 10 horsepower, which would be a pretty nice 130 kilometer an hour type of range. Yeah. Possibly, we'll see. I would suggest just doing a secondary battery. Maybe not the full thing, but another one that we could collect in, lay it in. This will fit right inside of the battery box horizontally, so you can just fit another one beside it. However big money allows, basically. The more you add, the longer you'll go. As I project, at 3,000 watts, this will go, which is higher than your cruising draw is going to generally be. You're going to get an hour of draw, 3,000 watts, and so you're going to be seeing fairly good distances. This will at least reach the 70 kilometers that it was rated at originally.
What it was supposed to get, yeah.
Yeah, so
it's totally fine.
This is a 4 amp hour larger battery than the one that he was supposed to get, which ironically is over there. And
yeah, so that's the battery that we took out of. It was in a battery box and everything. We had to pry it open. It was all glued shut and everything. Those are the ones that were in the bike, which was really surprising when we actually saw that they were lithium ion.
Looked like a decent cell.
Yeah.
We pulled a few out, two different series rows we pulled out, and we're going to actually test them right now. So far, they seem like they were used cells, traction abused, don't even hold a charge, their voltage jumps all around. So ultimately, we were hoping we could just use that as the plug-in if they were good.
Yeah.
The issue we found, one of the charger wires was disconnected when we opened it up, so we figured, hey, maybe it's You know, just something.
Yeah, so we were surprised when we saw this, and it looked like a really decently constructed battery and everything, but we did find the charger wire was disconnected when we pulled it out. So, and we thought, I mean, hopefully that was the only problem, that this was actually a really good battery, and that we could actually link it with this one and create some serious power.
Same thing we were planning on doing, except it would double the size almost. This one's a little bigger than that one was rated to be. It could run a higher watt motor, but you want it to be running cool, not heating up. You get better efficiency, better distance, all that kind of stuff. So this is where it's sitting. That's kind of the ideas with series versus parallel. The first cell obviously is just 3.7 volts. So you can see, and it's 3.6 to 3.7 is nominal voltage. You add another one in, and it doubles. You add another one in, it adds 3.7 more. And you can keep going down the line. To the end, we ultimately have, I gotta click this up one, close to 72 volts across the pack. So you can see that. That's the nominal voltage. It'll ultimately be higher. It goes up to 84 when it's fully charged, down to 60 when it's fully even when it's fully discharged. And then that'll shut down, and basically your battery life's gone. Mm-hmm. The battery's going to run with the electricity. Basically just flows this way, doubling up the voltage at each turn, 3.7 more volts as it flows through in this pattern. The series connections are, well, the parallel connections either this way, basically automatically will even out the voltage. So you have no concerns with the voltage being different between the cells in a single parallel run, because they'll automatically basically just, as pressure builds, which is voltage, if pressure is higher in one, it's going to leak over to the other one, and they're all going to auto balance out across the way. Series connections don't do that though, so as it flows this way and you're charging and discharging, they have the potential to start to get imbalanced, where this is 3.7 volts, this one's 3.9 volts, this one's 3.4 volts, they're all different. And so the BMS on top basically manages how each parallel group is charged or discharged in that series run. These are the balance wires that come out of it, and they're basically reading through this input. They're basically reading the voltage at each junction. And I have half on this side, half on that side. So they'll be able to read, and as it's charging, distribute the charge in a way that keeps them all at the same voltage. If one's too high, it'll shut down charge into that section, even discharge it into other sections if necessary, but it won't naturally do that automatically. The BMS that we have, we picked a 90 amp BMS because the original thought was to have one that'll be high enough amperage to not have issues. In this case, say that you wanted to do a 8,000 watt motor, and in order to do that, it's at 72 volts. The draw that you've got to have is that amount of amps capable. My initial thought wasn't that. I was initially aiming for a 5,000 watt motor based on what the Inja had told me, which 70 amps, 90 amp gives a little bit of room. You want to be able to protect your battery but not be limited, or not be limiting your battery, so we put 90 amps in. The initial thought when we saw the other battery was, ooh, add it on. So it got my brain thinking we should aim for a higher output at the end of the day. I hadn't connected the BMS fully up yet. And so the thought now is use the BMS just for charging, and then the discharging can happen without being balanced. And then when you charge it, as long as you're not going below 60 volts, generally you're not going to be risking any of the batteries. And then when you're charging, it'll just rebalance all the cells out, and so it'll discharge, maybe be slightly imbalanced at the end of the discharge, but the charge will balance them all back out. What that allows you to do then is bypass the discharge amperage, which is the high one, and then this is only needed for the charging, which is going to be 5 to 6 amps depending on what charger you get. The one he has right now is a 5 amp charger, so no risk at all to the battery in that, or to the BMS, battery management system in that case. There are two kinds of BMSs that you'll see. There are 2 wire BMSs, which is what this one is, and there are 3 wire BMSs in some cases. They all have a B minus, which is the battery minus. You just connect the battery into that from the negative terminal, and then this is able to, basically as it's charging, it'll charge through here. If it's discharging, it'll discharge through here. The charger minus usually goes straight to the charger alone, and then there's a P minus, which usually goes to the load, so the motor. In this case, it's a 2-cell or a 2-wire BMS, so this would be for charger and discharger both out of this one port, rather than having them separated where the charger negative came out here and then the power negative came out here. Notice there's no C positive, B positive, P positive on here. All the positive comes straight out of the battery. This will go and it'll split, and one will go to the charger, one will go to the discharge, which is the load or the motor or the controller, whatever the application is. So that's going to be just straight to the power. And then the negative is the only one that actually comes through the BMS. As far as the balance wires go, they're connected in a specific way. The first one coming off of the port number 1, which is right next to the, well, it's usually black, but it's the first one off this on the right hand side, goes straight to your 1 negative cell. Then the rest of these ones in red, and even here, this black one, it's just they made it 2 different connectors, but it continues the same idea. All the rest of these go to the positives. So this goes to 1 positive, which is here. Second red one goes to 2 positive, which is here. Then we go to 3 positive, which is here, and 4 positive, and 5 positive, and 6 positive, 7 positive, 8, down the whole line until you get to the 20 positive, which ends right there. All I gotta do now is just kind of control the wires, tame them down, so that it's able to be maintained within that. That pretty well kind of walks through the idea. You want to try to keep heat off the cells. If you heat the cells up, they're losing some of their capacity, lifespan, cycles that they can be charged or discharged. So you usually want to do spot welder on the surface of the cells, on the ends of them. And then if you want to connect a wire to it, you can just wire it off the center of it. So all the soldering that I did was between cells, not necessarily on a cell. So even though it's labeled as 1, 2, 3, 4, 5, 6, let's say 6 positive here, I didn't put it on the 6 positive, I put it on the between the 6 positive, because these are connected, they're electrically the same. This here and this here is going to have the same connection no matter where you put it. That's kind of it. The only thing we got to do really is run negative off. I'm going to split this because I was originally going to run it through and charge and discharge. As we started talking about higher power, I'm going to run another wire off here, so this can go straight to the load. So my load's going to be connected from here to here, so it's just going to discharge through the battery unregulated. There's going to be people saying that's a bad idea. It just depends on how careful you are at not running the battery super low. The only risk you really get is you decrease the number of cycles the battery can go through, charging and discharging. So we'll run one through, negative, this will connect straight in. The rest of them will connect from here to here. There'll be a charger, and then, so it's going to be just a charger wire like this, and a discharger wire like this. So we'll have 2 wires coming out, 2 connectors with 2 wire, positive and negative in each. And we'll just put that, I've got some heat shrink here.
Yep.
And once all the wires are in, we've made the expansion connections at the bottom, which will be just in a couple of days, the latest. Let's just go over the top, heat with a blow dryer or heat gun, shrink it on down, and it's all protected and all that kind of stuff.
It's a solid final battery after that.
So that's all that's left, and that's what kind of this process we got through to get us here. I do have a wiring diagram for what a BMS looks like. You can find those online. In this case, they have a P-, not a C-. Generally, it's a B-, P-, C-, or the 3. And you can find those all over the place. They're all over the internet.
Yep.
And they're all the same idea, and it's wired the way this one is, aside from the fact that we're bypassing the discharge, which the original battery did in the first place anyway. So it's not a downgrade in any way from what was originally in the specifications. This happens all the time. It just allows your BMS to not be the bottleneck point where heat starts to build up. The design of the battery is pretty narrow, so the heat should dissipate pretty well. We did use hot glue between them. You could use and that one there, you can see that it has the little spacers that keep the batteries held apart. But it was then sealed, put inside of a metal case with insulation on the side so it didn't rattle around. So no heat dissipation was occurring either way. This one's narrow enough that the heat, as it gets to the end, is going to start to slowly make its way out, so it's not going to build up a ton. So it's a pretty heat efficient design, even though it's hot glued as it changes. It just keeps it real compact. I mean, the weight of this battery is about 30 pounds.
Yeah, heavier than you'd expect.
Yeah, it's pretty dense.
All right, so we're going to pull up AliExpress for you. That's where we got the batteries, the individual cells. We got 240 of them initially, but then we ordered another 20 because it does take about sometimes a month or so to get these. We didn't want the batteries to come and then there be a couple defective cells in there, and then we can't actually end up finishing the battery within a timely manner. So we went ahead and ordered an additional 20 just in case there were a few cells that were bad in the 240 that we ordered. And all of them actually turned out to be good. We tested every single one. All of them seemed to be good. And so we added the last 20 that we got, the extras, onto it. And that would extend the range, right? The 20 we added.
Yeah, that'll extend the range and it'll reduce the amount of strain that each cell gets because the amps that each one has to move decreases. So you're looking at 3.2 instead of 3.3 or 3.4 that they're each pulling on a normal 3,000 watt motor.
But yeah, so we did order most everything off of AliExpress, a couple things off of Amazon as well.
Yeah, they had a good deal on the nickel strips on Amazon that were pure nickel. You can get scammed so fast through AliExpress if you're not paying attention. Kind of a case in point. Inja is a good case study.
Yes, sir.
So when you're looking for batteries, obviously there's a lot of fake claims that are made.
Yes.
A lot of like 18650s say 9,900 milliamp hours, which is absurd. Nothing can really be higher than the high 3,000s, even like a super good cell. So be careful to look at reviews, look at ones that are written about what their actual capacity are. These ones had plenty of images of internal resistance, the capacity of them each, voltage that they're sitting at after discharge. So we ran our own tests on them, which you'll see. And so we had similar outputs to these. They were right around 3,400, so they were exactly what they had claimed to be. A lot of them are fake, so you have to be careful on those ones. Yeah, so those are the batteries. That's the most important thing. I'm sure that Inja can give you a full parts list of everything that was used.
Definitely, yeah. So everything will be linked in the description. All the AliExpress links we used, exactly what we bought, will be linked in the description. We did buy the nickel strips off of, or it's just rolls.
Yeah, it's a roll. It's a strip. It's a strip of roll.
Right.
You can get it by the kilogram. The project that we used only needed about $35 worth, but a kilogram is like $80. And so it would be more efficient to buy that way. We didn't.
Didn't we buy the strips off of AliExpress and it turned out
originally, yes. We bought some from AliExpress labeled as pure nickel. You can test pretty easily. I mean, you get it out and it feels a little bit stiff, and then there's ways you can like scratch it, and if it starts to rust in salt water when you scratch it. But we just got a grinder, and if you hit it with a grinder and it sparks, you have steel in there. If it doesn't spark, it's pure nickel. So we tested it sparked, so we didn't use those ones. We bought some more off Amazon, which actually was just as cheap. Without being scammed.
Ironically, yeah.
So.
And it was actual pure nickel. So that was the one thing though that we did kind of get, like, they took advantage of us just a little bit, hoping that we wouldn't notice, right? So we ordered that.
They're nickel plated, so you don't look different.
Right. So we ended up buying the actual pure nickel strips off of Amazon. Yeah. So definitely be wary though, especially batteries. I would recommend, if you're gonna do this exact same thing, just buy these exact same ones.
These batteries are solid. They got good capacity, cheap as far as the cell goes.
Yeah.
And the seller didn't lie about any of the specs that were listed there.
And there were a lot of different battery options that we were looking at, even assembled units like this that would put out the same kind of specs, but they were too cheap to be realistic. So I would say those probably aren't going to actually
still
meet
cost
the specs.
more, and they weren't at this capacity. And the total cost of the cells in this case was only like 500 and something.
Yeah, it was like 500.
Fairly cheap, and the BMS is relatively cheap.
Yeah.
So you can't get a 44.2 amp hour battery for that cost. So it's a real solid build.
Yeah, definitely. But yeah, everything's gonna be linked in the description if you guys actually do want to replicate this. So we're the first thing we're gonna do is just stick this in the bike and see how it performs. Of course, we're gonna try to code or reprogram the controller and everything as well. But we're gonna still use a 3,000 watt motor.
We're gonna skim through anything that's bottlenecking it.
Right.
There's some suspicion about where power is being stuck at. The battery, after having tested those cells, was amazed that it even put out as much as it did based on the couple that we're working with.
These were
so this will be a big improvement. But from there we can see where it's being bottlenecked. Cut out, replace fuses for higher watt ratings. I mean, figure out where it's all happening at and just get it tuned up and ultimately
see where we go
from the battery to the controller. What else might we want to upgrade? Who knows?
Yeah, that's pretty much it.
Signing off.
Signing off. All right, well, we just finished, fully finished, right? Fully finished the battery. That's it. Good. So we can literally plug this in to the bike right now.
Yeah, we decided to not deal with any expansion ports right now, but eventually it's probably gonna, if we do another set of cells on here, you can just slice this off, pull it off, and then you'll just have to rewrap it at the end. I did just zip tie all these together so that it kept everything in place, but we have our discharge cables and our charge cables. And so we use the same connectors that the original battery was using, so it'll plug straight in.
Yep.
And all we gotta do then is we'll get in there and charging and see how it sits and works, but we'll eventually, just before it's written, have a thing that'll hold it in place so it's not sloshing around in there.
Yep.
It's a little more efficient than the
that's the next step, is actually putting this in the bike and getting it all situated. This is the exciting part.
Powers it and
get
it charging.
Yep. Then we can run some tests, some first initial tests. Yeah, even so, full throttle. That's freaking faster. Holy that's way faster. Definitely quicker than before. We're at 50 kilometers and climbing. Yeah, it's definitely a lot quicker than it was before. All right, guys, well, that's gonna wrap it up for this video. Thank you for watching. I know it was pretty long, but I hope you guys enjoyed it and that it was very helpful for you guys. If you enjoyed the content, feel free to smash that subscribe button. I do have more videos coming on this series, and I'm sure you guys will love it, so I'd hate for you guys to miss out on that. So I'll